Every single API call made across your entire AWS footprint must first pass through Identity and Access Management, or IAM. As a global service, IAM operates as the central control plane for authentication and authorization. Within this perimeter, a single loose programmatic key or a poorly structured JSON policy statement can expose an entire enterprise database to the public internet. This engine evaluates identity metadata against a JSON policy parser and a secure credential store to validate requests. Once validated, it routes down one of two pathways: human interaction via the management console or machine automation via programmatic interfaces. Securing these pathways requires engineers to master core identities, complex JSON policy grammar, physical hardware constraints, and auditing telemetry tools. Mastering IAM is about more than facilitating logins. It is the process of systematically eliminating unauthorized access at the mechanical level. When you create a new AWS account, you start with a single root account. This is a default identity with complete access to every resource and billing construct, and it cannot be limited by IAM policies. Because it bypasses all policy controls, standard architectural guidelines require that you lock away the root account credentials immediately. They should never be used for daily operational tasks. For those daily tasks, you create standard IAM users. You must maintain a strict one-to-one mapping. One physical developer equals one unique AWS user. Sharing an IAM user destroys the forensic auditability of AWS CloudTrail, making it impossible to trace specific actions back to an individual. This comparison matrix details the separation between IAM users and IAM groups. While users hold actual credentials like passwords and access keys, groups are purely logical containers used to apply permissions at scale. Groups have no distinct security credentials of their own. There is a rigid constraint built into this architecture. Groups cannot contain other groups. Nesting is blocked by the IAM control plane. Maintaining flat, unnested groups and strictly mapping users to physical individuals prevents permission sprawl, ensuring you can account for every action taken in the environment. The permissions attached to those groups are written as JSON documents. This grammar dictates exactly what an identity is allowed to do within the environment. AWS operates on a strict default deny posture. If an action is not explicitly allowed, it is denied. If an action is explicitly denied anywhere in a policy, that deny overrides any overlapping allows. This JSON policy block outlines the mandatory elements of every statement. The effect must declare either allow or deny, the action specifies the target API calls, and the resource identifies the specific infrastructure being targeted. You can target broad sets of API calls using wildcard characters in the action array. The resource array requires precision, using Amazon Resource Names, or ARNs, to target exact storage buckets or compute instances. When attaching policies directly to a resource rather than a user, you must define who the policy applies to. This requires a principal block, which is mandatory in all resource-based trust policies. Above all of this, the policy language version must be defined exactly as the string 2012-10-17. Any deviation causes AWS to parse the document using deprecated legacy rules, changing the way variables and wildcards are evaluated. A single malformed line in this grammar can create a security gap that persists until the policy is manually corrected. To defend against credential theft, you must implement global, account-level password policies. You can enforce high-complexity rules, mandate strict expiration cycles, and prevent historical password reuse. For higher security, you must implement multi-factor authentication, requiring developers to supply a rotating code from a physical hardware device alongside their standard password to securely access the management console. This matrix categorizes the supported MFA options. While virtual MFA applications provide a software-based defense, higher security tiers require dedicated physical hardware. U2F security keys, like the YubiKey, offer a scalability advantage. A single physical key can store multiple security tokens and authenticate multiple user profiles across different AWS accounts. For isolated environments, standard hardware fobs provide standalone digital tokens. For sovereign cloud deployments, AWS supports specialized fobs designed to meet FIPS compliance standards for GovCloud. Enforcing hardware MFA ensures that even if a local password is stolen, attackers cannot access the control plane without physical possession of the device. Human console access is only one pathway. Automation scripts and headless applications require an entirely different access mechanism. Programmatic access bypasses the web console completely. Instead of passwords, applications rely on static variables, an access key ID, and a secret access key. These static keys do not automatically expire. They remain active until an administrator manually revokes them. Committing these active keys to public code repositories remains a frequent cause of security breaches. This flow illustrates how developer tools, like the AWS CLI or language-specific SDKs, bundle those static keys within the application to generate an HTTPS signed request, which is transmitted directly to the AWS public API. AWS uses your programmatic credentials to cryptographically sign every request, verifying the signature at the endpoint before the command is executed. Because these keys provide silent, direct access to the public API, they require a stricter governance posture than standard passwords. Under the shared responsibility model, AWS secures the physical infrastructure, but managing policy composition and key rotation falls entirely on you. You cannot rely on manual audits to maintain this compliance. AWS provides two specific diagnostic tools to manage this. On the left, the IAM Credentials Report outputs account-level telemetry on the status of all passwords, MFA devices, and programmatic keys. Security teams use this data to detect inactive credentials and isolate stale accounts for deprovisioning. On the right, the IAM Access Advisor operates at the identity level. It maps granted permissions against their last access timestamps, revealing services that are authorized in the policy but never actually used. By analyzing this telemetry, you can systematically strip away unused privileges, aligning your actual usage with the principle of least privilege. Locking down the root account, mapping physical users one-to-one, adhering to flat group constraints, and enforcing hardware MFA creates a secure baseline for your identity infrastructure. However, configuring these boundaries is only the first stage of identity management. In a production environment, you must also manage how multiple overlapping permissions interact and resolve access rules when identity-based and resource-based policies overlap. In the next video, we will deconstruct the inner workings of the AWS Policy Evaluation Engine, contrast S3 bucket policies with identity policies, and analyze the IAM Pass Role API to securely delegate permissions to AWS services. Engineering an enterprise-grade cloud environment requires this level of control over the identity perimeter.